Well, thank you for coming. It's an honor to be here. I want to thank the organizers for the invitation. I am here this week as part of a week-long conference at the Niels Bohr Institute on transients in the universe and cosmology, and many experts are here with me from the conference. If you could raise your hand, experts from the conference. So if you have any questions about anything in this talk, they have the answers for you. And so please seek them out down in that corner. Anyway, so let's begin. So I'm going to tell you the story of how observations of exploding stars called supernovae revealed to us that we live in a universe that is not just expanding, that we knew almost 100 years ago from Hubble and Laureate, but rather accelerating, expanding faster and faster all the time due to a mysterious new component of the universe that we give the name dark energy. So before I can tell you how this discovery was made and give you an appreciation of it, let me kind of give you a crash course in cosmology. So we'll take a step back and just look at the universe. So when we look out at the universe, this is more or less what it looks like. This is the deepest image ever taken of the universe, at least at the time it was taken. And the way you take a deep image of faint sources, any photographer knows, is you keep the shutter open for a long time. So we kept the shutter open with the Hubble Space Telescope's advanced camera for about a month, pointing at a relatively blank spot on the sky. Now, that's sufficient to see objects here which are trillions of times fainter than what your eye can see, galaxies, tens of thousands in this image. Now, when you look at this image, it doesn't look like anything is moving. I mean, we kept the shutter open for a month. Things don't look blurry. So the impression you get of the universe is that it's static. But that's actually not the case. The universe is actually expanding like it received a big kick that we call the Big Bang. And now the separation between galaxies is growing. I generally say like a giant loaf of raisin bread. Perhaps in Denmark, I should say like a giant raisin pastry or something. But the idea is the same. The more space or dough there is between us and a distant galaxy, then the faster it appears to be moving away from us. There's no unique place in this giant loaf of rising raisin bread. Whichever galaxy you're sitting on, it will look like everything is moving away from you. So the question is, how do we really know that our universe is expanding? And the answer, of course, is we checked. So we had to make measurements to determine this about the universe. And so the question really is, how do you do that? How do you verify that this animation that I showed you actually is what the universe is doing? Well, if you noticed in the animation, there were objects, they were separated, and they were moving. So what you need to be able to do is measure how far away other galaxies are, so measure distances, and measure this aspect of their motion. So I'm going to talk to you a little bit about how is it that we determine how far away things are in space. And in order to do that, it's useful to sort of remember, how do we figure out how far away anything is? For example, here on the Earth. So here on the Earth, we have lots of ways to figure out how far away things are. One method, known as parallax, you may see a crew of surveyors out on a road. They're trying to measure the distance to that tree, but they don't want to swim across that stream with a tape measure in their mouth. So, instead, they cite the position of that tree relative to a distant mountain. They move their equipment along some baseline, and then they take another sighting that gives them a length at an angle, a triangle. It allows them to determine the distance. That's a great method. Another method we use is the method of lighthouses. So a ship captain at night wants to make sure they stay a good distance from the rocky shore, but they can't see the shore. So they look for the light of a lighthouse, understanding that a lighthouse is extremely luminous. So they're looking for it to look very faint to know that they are safe. They can gauge distance that way. But what if it's a foggy night, right? If it's a foggy night, it could fool them into thinking that actually they're still quite far from shore because the light is dimmed when they're not. Well, we have solutions for that too. We have things like foghorns, which operates by a similar principle, something that is intrinsically powerful is attenuated by traveling over distance and spreading. And so, you want to make sure in this case, the lighthouse looks both faint and the foghorn is very quiet, okay? Another method that we use, this one we use every day. I call this objects of known size. So every day we walk around and we see objects we are familiar with, whether it's cars or people, but they're miniature versions of themselves. And we understand that they look miniature because they're just very far away. And we use this fact to gauge distances. For example, here's a fleet of airplanes that you see, and you look at these very small versions and you recognize that those are much further away. I mean, if you didn't know much about airplanes, you could think these were baby airplanes and that these were all traveling together. But so it requires some knowledge, some understanding of the source that you're looking at. Now, unfortunately, we don't have any of these objects in exactly this form. These are all human-made inventions. However, we have other things in space. We have telescopes and we have objects that nature provides. And one of the things that nature provides is very similar to the lighthouses. So in a galaxy like this, which may have 100 billion stars in it, at some point in its life, one of those stars may die in a fiery explosion called a supernova. And when that happens, they are billions of times brighter than the sun. And so let's make a supernova go off, it appears, and the further away you place it, of course, the fainter it looks. So we call an object like this, whose luminosity we understand, but then we see it looking faint, we call it a standard candle in cosmology, a tool that we can use to gauge distances. And then it's just the inverse square law, that if it's twice as far away, it's 4 times as faint. If it's 3 times as far away, it's 9 times as faint, and so on. So one thing cosmologists like myself do is we look for these standard candles, things we recognize, and use them to gauge distances. Now, the other aspect you saw in that animation was the apparent motion of galaxies apart. How do we determine that that's going on? Well, generally, we collect light from those distant galaxies. And for example, even from standard candles, we can do that. And that light is generally emitted at a relatively blue wavelength that we know from the laboratory. But then as the light travels to us, due to the expansion of space, that light is redshifted to longer wavelengths, looks more or less like this. So this is known as the cosmological redshift. Now, it's similar to something you may have learned in physics called the Doppler shift. The Doppler shift, though, is when an object, an ambulance or something, is actually moving with respect to you. The key distinction here is it's not that the object is moving, it's that space is expanding. To the observer, it may look the same, that you still see this red shifting of light. However, the key difference is when space is expanding, it will affect everything that's out in space. And so if we look around us and we see a lot of redshifts, we could either think there's like a conspiracy that everything is moving away from us, or we recognize this as a property of the expansion of space. So when we look out at standard candles, then what we've learned is we can measure their distances, we can measure the recession of that galaxy as seen from the redshift that it has. So now let's return to this nice animation that I showed before of the expanding universe, except now we can get quantitative. We can actually go out with our telescopes and we can measure a series of distances and the recession velocity of the galaxies. And the signature, the proof that our universe is expanding, is to see a linear relationship between these two, because the further away something is, the faster it will move away from us if it is space itself that is expanding. Now, if the universe was expanding faster, this would be a steeper slope. If it were expanding slower, it would be a more shallow slope. It could be that the universe was contracting, we would see a negative slope. So we actually measure the slope of this relationship as a measure of how fast the universe is expanding today. Now, this is not just a thought experiment. This was first done by the astronomer Edwin Hubble in 1929. He combined measurements of redshifts that were made by Vesto Slipher with measurements that Hubble did from the 100-inch telescope at Mount Wilson, and he made this iconic graph. Now, I know this doesn't look that impressive. It probably looks like the physics lab you did in high school that didn't turn out maybe so well. But actually, this graph is just absolutely iconic. It's so important. I often tell my students I don't have any tattoos, but if I did get a tattoo, I think this is probably what I would get a tattoo of because, in my field, that's how meaningful it is. Now, of course, this was not the final proof. This was just the first evidence that the universe is expanding. Many of us have added to this over time. In my thesis in 1996, I used these exploding stars to measure greater distances. So you can see as you go further out into space, it's very clear, this linear signature I talked about. In fact, Hubble's original, what we call the Hubble diagram after Hubble, or Hubble-Lemaitre diagram, would fit in this tiny little red box here. So, certainly as we go to further and further distances, it becomes very clear. Okay, so you've learned enough to do a little cosmology. You're not ready for your PhD defense yet, but we are going to proceed with some of the tools we've built up now. And we're going to address really interesting questions like, when did the universe begin? So when I was a kid, I thought, if you want to know when the universe began, you asked a philosopher or a priest or a rabbi or something like that. But no, actually, this is a scientific question that we can get a real mathematical quantitative answer for. So now that we have determined that the universe is expanding and we've measured the rate at which it's expanding, and that rate is known as Hubble's constant, then we can imagine or use the power of mathematics to run this movie of the expanding universe backwards in time. So instead, imagine the universe contracting at the rate that we measured it to be expanding, and then just simply, through the power of mathematics, keep running this movie backwards until everything is on top of everything, okay? And that is what we could call the start of the universe or of this universe. And so that is the age of the universe, the time from now till in the past when everything was on top of everything. And to simple approximation, if the expansion rate has not changed too much over time, mathematically 1 over the Hubble constant is a good approximation to the age of the universe, okay? So that's great, and we're impressed with this ability. However, as the professor said before me, there's often been problems with this, connecting this cosmological estimate of the age of the universe to the terrestrial or, real life understanding of how old objects are in the universe. So when Hubble first estimated the Hubble constant, he didn't call it that, he got a number like 500, which converted into units of age of the universe would have implied that the universe was only about 2 billion years old. And even in 1929, geologists knew that the Earth was older than that. So this was the first time there was a problem, or what I might generally call a Hubble tension. And there's been more since. But an interesting thing about measuring this Hubble constant, this expansion rate of the universe, is it's really hard. And there's been a lot of progress and development in the effort, the almost 100-year effort now to measure Hubble's constant. This was a nice graphic from the New York Times a number of years ago showing the changing values of the Hubble constant simply by improving the measurements and the resulting age of the universe. So along the way, we learned critical things in order to measure the expansion of the universe. We learned that there have been 2 major generations of stars in the history of the universe. We learned to use better detectors in our telescopes, from photographic plates to CCDs. We launched the Hubble Space Telescope that got above the atmosphere and gave us pristine images. We learned to measure distances with supernovae. And in fact, there's been a lot of progress, particularly in the last 20 or 30 years, where we've gone from ranges even of 50 to 100 down to a pretty small range. At the conference that I'm at, I was presenting results on some of the most recent measurements of the Hubble constant and how they are telling us an interesting story already, but certainly telling us that the universe is relatively old and that we probably don't have the level of age crisis that we had before. Okay, so you know the universe is expanding, but you might be wondering, well, what happens next? I mean, does it expand forever? Does it stop? What goes on? Asking this question, thinking about it, a good model is to think about a thought experiment Isaac Newton did when he was understanding gravity, of what happens when you launch a cannonball off the surface of the Earth, let's say off a mountain, okay? And he thought through, the greater velocity you gave it, the further it would go. The Earth would eventually curve away, and if you gave it enough velocity, what's called escape velocity, then it would escape the gravitational pull of the Earth and go away. an alternative way to think about this is, given a certain velocity, if I shrink the mass enough of the Earth, there will be less gravity. And again, my cannonball can escape. So this question of what happens to something in motion when gravity is the main factor here has a lot to do with how fast is it moving and how much gravity, how much mass is there, okay? So thinking in that context was very different than the way Einstein came to this problem. Einstein was working in 1916, 1917 on the general theory of relativity, a new theory of gravity to replace Newton's theory that could explain or address the entire universe. And so Einstein was wondering himself what the fate of the universe would be. And so the first thing he did was he went to the astronomers of the day and he asked them, is the universe expanding? Is it contracting? What's it doing? And they told him incorrectly that it was relatively static, that the universe really wasn't expanding or contracting. The reason was because in their time, they didn't recognize that the galaxies that we see are actually outside the Milky Way. So they were mostly looking at the motions of stars around us and saying, they're not really moving all that much, okay? Now, this really perplexed Einstein because he realized that if you take a collection of masses like these galaxies here, even if they were static, then the gravity, the attractive gravity of the matter in these galaxies should cause them to start to fall together. So how could it be that the universe could really be static? He struggled with the mathematics of general relativity, and he made an amazing discovery, okay? He discovered that although the gravity of stuff, galaxies, planets, stars in the universe is attractive, just like Newton knew, that the gravity of empty space itself could be repulsive, okay? He called this the cosmological constant, and he thought this must explain why the universe is static, that it's not expanding or contracting. These two kinds of gravity, the attractive gravity of stuff and the repulsive gravity of space, must be in a perfect balance somehow, holding this static. Now, today we would call the gravity of empty space dark energy, and this would have been a beautiful idea, except it was totally wrong. Einstein hears 10 years later that Hubble has shown that the universe is expanding. He goes to visit Einstein at Mount Wilson. Here's a nice shot of Einstein and Hubble and others at the observatory. And, you know, the famous story is he visits Hubble at the telescope, becomes convinced of the accuracy of the data that Hubble is studying, and therefore calls this invention of the cosmological constant the biggest blunder he's ever made. That's the famous story. I like this particular picture, but I've come to realize this must be a posed like PR shot. The reason is because even in those days, the objects Hubble and others were looking at were so faint that you couldn't see them with your naked eye. You'd have to use a photographic plate and add up light for hours. So there's no way that Einstein can actually see whatever Hubble was studying. But, you know, it's embarrassing to admit you can't see. So you say, yeah, I see it. And, you know, it seems unlikely that Hubble would have a pipe at the observatory. So I'm just convinced that this is a PR shot, but it's a great picture. And it conveys the idea of somebody being convinced of the accuracy of data. Okay, but the idea of this cosmological constant has always lingered because the math was good, just the physics didn't seem to be right, okay? So therefore, okay, so if not static, if the universe is expanding, again, let's go back to the analogy of the cannonball being fired off of the surface of the Earth. What will happen? Will the cannonball escape the gravitational pull of the Earth? Will our universe escape its own self-gravity? So if this were something that moved along quickly, like the stock market, we could just watch over time and sort of see how it evolves. But the process is extremely slow. So therefore, we can't just wait and learn what trajectory the universe is on. Instead, we use a trick, a really interesting trick that cosmologists, astronomers have known forever, which is when we look out at distant objects, we are looking back in time. And so what seems annoying, this kind of built-in delay, is actually very powerful. The fact that the universe does an instant message. So when I told you before we were measuring how fast the universe is expanding, I wasn't totally accurate. What we actually were measuring was how fast the universe was expanding a little while ago. So we may look at a distant object and there may be a built-in delay of the distance divided by the speed of light of 1 billion years. So this may tell us how fast the universe was expanding in the past. Then we look at a more distant object, and it tells us how fast the universe was expanding 2 billion years ago, and so on, 3 billion years ago. This is a powerful way to look at the past trajectory of the universe, like looking at that cannonball and seeing whether it is decelerating enough to fall back to Earth or whether, it will have escape velocity. So in the early to mid 1990s, most astronomers thought that the most likely possibility was one of these two. Either that the universe was a very heavyweight universe, chock full of matter, and that in the units that we measure, omega matter, more than one, implied that the universe had so much gravity that it would halt the expansion in the future and cause the universe to turn around and recollapse in something like a big crunch, the opposite of the Big Bang, okay? Or the other possibility is we lived in a lightweight universe, in which case there was very little matter, there'd be little deceleration, and that the universe would expand forever. So again, this is the cannonball with escape velocity. This is the cannonball without escape velocity, except now framed in terms of what the mass is of the universe that would cause this, okay? So by the 1990s, astronomers knew that they wanted to go out and measure this past trajectory and see whether the deceleration was strong or weak, hence whether the mass of the universe was big enough or not big enough to stop the expansion. Now, it turned out to do these measurements, you needed to use supernovae to measure great distances, just like I described, but not any kind of supernova will do. There's a certain subclass of supernovae called type 1a, whose physics was sort of first understood by the famous Indian astrophysicist Chandrasekhar in the 1930s. Chandrasekhar showed that the core of an old star called a white dwarf could only be stable up to a certain critical mass called the Chandrasekhar limit, 1.4 times the mass of the sun. Anything bigger than that, and you will get a runaway thermonuclear explosion. So somehow nature produces these explosions with a white dwarf and certainly some other kind of donor star that donates material to the white dwarf by gravity. The details of how this happens are still unclear, but somehow or other, something around Chandrasekhar's limit is reached and an explosion occurs, which is about as bright as 4 billion suns. What's so great about these is they make great standard candles because they always blow up roughly around that mass scale set by Chandrasekhar, and they can be seen about halfway across the universe. So really, really great tools for this. So in my thesis, I started studying these, and a big question people often ask is, how do you find the supernovae? And if you look for the bright spot at the end of the arrow, that's where the supernova is. No, I'm just kidding. We add the arrows. You actually do have to find the supernovae. And so how do you find a supernova when you don't know when one will explode? Well, first you look at this as a statistics problem. It's incredibly rare. In our galaxy, there will be a supernova about once a century, just on average. In fact, it's been a number of centuries since we've had one. So if you just pick your favorite galaxy and stare at it, you're very unlikely to be successful. It's kind of like playing the lottery, though. You eventually realize the way to win the lottery is to buy all the lottery tickets, right? And so that's what astronomers have learned to do, just by beating the odds. Instead of looking at one galaxy, let's look at 100 galaxies in a year. Oh, now we're likely to find one supernova in that year. Oh, let's do more. Let's look at 1,000 galaxies. Now we'll find 10. And we've gotten this to an ability to find them whatever day of the week we want to find them, because we take wide enough images that contains hundreds of thousands, if not millions of galaxies. And so one of those is bound to have a supernova explode in the next 30 days. And so then computers are very good at allowing us to take a very wide image, take a second image a month later, and digitally subtract them, align them, match them in every way, and then send us alerts when there is a new point of light seen. And so this technology really first came of age in the late 1990s with wide field imagers and computers just powerful enough to do this. So my colleagues and I formed a team called the High Z Supernova Team in 1994, thinking that we were going to measure the deceleration of the universe. As I described, it was either going to be decelerating a little or a lot. And so we were going to measure just how much. And so we collected our first batch of data. I was just a postdoc at the time, and I was picked to lead the analysis of the first big tranche of data in 1997. And so I began analyzing the data, not yet realizing that anything really surprising was going on. And so I was looking at what was a very simple equation in the units that we were using, that the amount of deceleration of the expansion, a term we call Q naught, is directly related to the mass of the universe divided by 2. That's pretty easy math to do, right? So I wrote a computer program that, having analyzed the data, to convert the deceleration of the universe into tell me what was the mass density of the universe. Because I was impatient. I wanted the answer. What is the mass density? Then I know what the ultimate fate of the universe is. So this is the key page from my lab book. I wrote the program and I had it spit out the value of omega matter. And this was the shocking thing. It was negative. Okay. Now there's no such thing as negative mass, but computers don't know physics. So you just tell them this is the equation to fit, and they say, okay, I'll do it. So I hadn't yet noticed that the universe was actually accelerating in our data, that the sign of this is negative. And so therefore it made this equation be true just by reporting a negative mass for the universe. So, realizing, hey, that isn't even allowed, that isn't good physics, right, made me think a few days later about introducing Einstein's cosmological constant. The only thing we know of, or something similar, that has the ability to change the sign of this equation, that can allow the deceleration to be negative. That is, to allow the universe to accelerate. The only term that has the ability to do this is something like Einstein's cosmological constant. So, a few days later, thinking about that, calculating the likelihood that that was required, and even for very little matter in the universe, the data required a cosmological constant at something like what physicists would call 4 sigma, which is an interesting indication that something's going on. So then, after doing a lot of cross checks, it was time to start talking with my colleagues on my team. And I always think this is very interesting. I like to show you the email discussion that went on over 24 hours as our small team first came to grips with this. And, it's interesting to see how scientists react to something as surprising as this. So we were spread over 4 continents. And so the first person to write in was Alex Filippenko, who's a very famous astronomer at UC Berkeley on our team. He wrote, Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Okay. Bruno Leibengut, who is a colleague of ours in Germany at Garking, concerning a cosmological constant, I'd like to ask Adam or anyone else if they are prepared, if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. So, there's a real conservatism that which you could certainly understand. Brian Schmidt, my colleague who was down in Australia, who had led the efforts to find the supernovae, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. My thesis advisor, Bob Kirshner from Harvard, was on sabbatical in Santa Barbara, and he wrote, I am worried. In your heart, the cosmological constant is wrong, though your head tells you that you don't care and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. So, my colleagues know that the cosmological constant had come and gone, a number of times in the past to solve problems. So it was like, oh my God, you're not going to the cosmological constant, are you? So, this was kind of nerve-wracking. Mark Phillips, great astronomer in Chile, as serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry in Hawaii, who remembers the detection of the magnetic monopole and other gaffes. On the other hand, we should not be shy about getting our results out. So every physicist carries, a kind of library in their mind of all the times that something was claimed and was not right. And so, you don't want to just be something else on that list. Alex Filippenko was very ambitious. If we are wrong in the end, then so be it. At least we ran in the race. What race is he talking about? there was another team at the Lawrence Berkeley National Lab, just up the hill from me at the time, led by Saul Perlmutter, that was doing the same experiment we were. And so, there's the competitive nature of, okay, what answer are they getting? We don't want to be last in this. We're competing for telescope time, so let's keep moving ahead. I came back from my wedding, was packing my bags for my honeymoon, and dashed off an email. The same 24 hours. The results are very surprising, shocking even. I've avoided telling anyone about them because I wanted to do some cross-checks. I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers, after all. Alejandro Colciati from Chile. Well, if Einstein made a mistake with the cosmological constant, why couldn't we? Wasn't very reassuring, but I got his drift that, we'd be in good company at least. Nick Sunset from Chile. I really encourage you, Adam, to work your butt off on this. We need to be careful. If you're really sure the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have a scientific result that is more exciting come your way in your lifetime. So there was certainly an appreciation on the team that this was really profound, but also a great worry about getting it wrong. And I think that, that's sort of what you would expect. But we went ahead and published this paper, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant. In other words, that the supernovae we had measured nearby and far away indicated that about 70% of the universe was in this form of dark energy and that it was accelerating the universe. And the other competing team reached the same conclusion in the same time frame. And so this was very exciting to the community. This actually became the breakthrough science of the year in 1998, implying that, Einstein himself would have been pretty amazed that, this idea he had, this mathematical term he had, that he had brought in to solve a problem, then threw it out when he was basically given the wrong information, was back and actually was the dominant thing in the universe. Okay, so that's great, but the truth is, we don't really, even though Einstein had this mathematical term, we don't know the physics of this dark energy or this, why is the universe accelerating? What does this really mean? Okay, so we don't know, and so this is actually one of the very biggest problems in cosmology today. You hear people talk about it all the time. There's all kinds of designs and projects and plans to address this. But the basic best three guesses in order, I would say, are that it is what a quantum physicist would call vacuum energy. So that in quantum mechanics, there is a basic amount of energy, a 0-point energy of space that you can't avoid. So it has to be there. And so that's a great idea in quantum physics. Now, you talk to somebody who studies general relativity, and they will say, yes, if there is such an energy, that will cause the universe to accelerate. It has repulsive gravity. Absolutely. So they're both very happy until they start talking numbers, because to the quantum physicist, the value we see is 120 orders of magnitude bigger than what would make sense, what they would expect. And so that's a serious mismatch. And so although we have two wonderful ideas that seem to work, the quantitative match is so horrendous that we just don't feel very comfortable about that, okay? Another option is that there's a field in space we didn't know about. You could think of any field a magnetic field, electric field. This is a different field, but there's energy associated with a field, and that field might be temporarily mimicking static energy in space. The difference is a field can change, a field can go away, it can evolve. It wouldn't be actually a property of space itself forever. And so that's a possibility. Another is nobody's ever applied gravity across the entire universe on the longest range scale. So lots of theories break down when you get to certain scales. So maybe we've broken Einstein's theory of general relativity. So by the late 1990s or early 2000s, we weren't really thinking about these three options. We were more worried, what if we're just wrong? What if the universe is not actually accelerating, but somehow we were getting fooled, that the distant supernovae we were looking at with our telescopes looked dim, not because of dark energy, but because of these effects I talked about earlier. There can be dust or fog in the universe, just like on a foggy night. Or what if we are looking so far back in time that these supernovae are just born fainter, that the universe was different then? So in order to address that, well, here's the idea. So when we looked with our telescope at a distant supernova, it was faint, and we said that means it's far, and that led us to think there was dark energy. But an alternative explanation was that there were these, there's kind of hypothetical clouds of dust throughout space. Nobody had ever seen these before. in intergalactic space, but nobody had ever seen dark energy before. So people hypothesized things like this. And so we had to test this possibility that something that was faint meant we were actually looking through the fog of intergalactic space. And so the idea then would be to find even more distant supernovae than we ever had, because if we found more distant ones, and this were true, we'd look through more and more of this fog, and it would amplify the effect. Whereas if what we were seeing was really due to dark energy, the cosmology predicts that when the universe was younger, it would have been more compact, and so matter would have been far more important than dark energy. We would see this effect sort of level off and go away. So to discriminate between those two possibilities, we needed to find supernovae that were more than 5 billion, maybe up to 8 billion light years away. We needed a new way to find the supernovae, that only a really special telescope would allow us to find those. So here's a crash course in the history of improving telescopes since the time of Galileo. So this is the improvement over your eye. Galileo got us the first factor of 100 in improvement of the telescope by increasing the aperture size. And then over the course of centuries, we built bigger telescopes, we put them on mountaintops, we built them with better detectors than our eyes, like photographic plates, electronic detectors, and then finally, we figured out how to put them in space above the blurring effects of our atmosphere. And so this is what it looks like when you try to observe a distant supernova and its host galaxy, seen from the ground and then seen from the Hubble Space Telescope. And then sometimes we're really lucky. The astronauts returned to the telescope. They put new detectors in. That happened most recently in 2009. Or we build even better telescopes. Here's the JWST, which is getting us a clean factor of 1 trillion over your eye. But the point is, we needed to change our methodology to actually search for these ultra-distant supernovae using the Hubble Space Telescope. And so that's what we did over the next several years. The astronauts had returned to Hubble, and they had put the advanced camera and wide field camera 3 into the telescope. They were more powerful. And from 2002 till about 2014, I led an effort to find supernovae at redshifts greater than 1 all the way up to redshift 2. So again, you see the arrows pointing at the supernovae, the before pictures and the after pictures. And with this data, we were able to rule out this alternative hypothesis and conclude that, lo and behold, yes, the universe was decelerating in the beginning when it was more compact, when it was dominated by matter, most of it dark matter. But then as that matter thinned out, as the universe expanded, this dark energy has sort of been waiting in the wings, and it has been pushing the universe apart. So now the universe is expanding about 20% faster than it was just 5 billion years ago. So in science, we never really believe anything from just one technique or one method. We really become convinced when there are many different methods that converge. And so in 1998, that was the first real observational evidence that we had that the universe is accelerating and filled with dark energy. A few years later, in 2003, astronomers saw another effect called the integrated Sachs-Wolf effect, which means that you looked at photons of light from the early universe, from the cosmic microwave background, and as those photons of light approached clusters of galaxies, they would gain energy as they fall into the gravity wells of those, and then they lose that energy as they climb back out. But dark energy actually is opening up these potentials, and so they don't end up losing as much as they gained. This effect was seen in 2003 and confirmed the picture of dark energy. Then by the early 2000s, astronomers had measured the cosmic microwave background radiation, which revealed the geometry of space, which tells us the total sum of all matter and energy in the universe is 70% more than just the matter part that astronomers had been able to identify. So the 70% here matched the 70% here, matched the 70% here. And then we see on the largest scales, large clusters of galaxies are becoming less effective at pulling in new galaxies due to gravity, because the dark energy, even on those scales, is pushing out. We've seen a change in the absolute scale of the universe from the cosmic microwave background to the present that wouldn't be possible if we didn't have this dark energy speeding up the acceleration. But the way we were ultimately absolutely convinced that the universe was accelerating and that there was dark energy was that we won the Nobel Prize. So you go to Stockholm and they tell you it's right. And you're like, oh, what a relief. Anyway, no, but we had, a nice time in 2011. We won the Nobel Prize, and our whole team came out and the other team came out, and, we all enjoyed this. And, it was really fun, but there was a, kind of a dark side to all this merriment. And so this was nicely exemplified in this show called Big Bang Theory, which kind of made fun of us on one of their episodes shortly after. And if the sound works, I'm going to play this episode here.
2 a.m. What are you doing up?
Hold on.
2 a.m. What are you doing up?
Nobel Prize acceptance ceremony streaming live from Stockholm.
Sure. I want to see what all the scientists are wearing this year.
Look at these men. They've managed to win the top science prize in the world with no more understanding of the quantum underpinnings of the expansion of the early universe than God gave a goose.
Right, so exactly what he said is true, that we do not have a deep understanding of the quantum underpinnings of gravity that explains this phenomenon. We are just observing it. So we are open to this criticism because we are all, as a community, open to this criticism that, that we observe the universe accelerating. We name it dark energy. We even sometimes say there is a cosmological constant, and yet we sort of sweep under the rug this 120 orders of magnitude problem. So, it's a serious problem. Now, as we continue to work on this problem, there are other interesting clues which have been emerging. This is one of the ones I was talking about at the conference that my colleagues and I have been looking at for 10 years now, which goes by the name of the Hubble constant tension, a little bit like what I talked about before. See, if we understand the universe, we can map its whole trajectory. There's a period where it's dominated by dark matter, and so this is the expansion rate of the universe over time. And so it slows in the beginning, just like the cannonball, because of the gravity, the self-gravity of the universe, before it thins out enough, and then dark energy dominates and it expands. Now, that's great. And because we also have observations from the Big Bang afterglow, the cosmic microwave background, that tells us the state of the universe shortly after the Big Bang. And then by understanding the physics of the universe and its composition, we should be able to map out this whole trajectory. And actually, we should be able to predict how fast the universe would be expanding today based on how it looked shortly after the Big Bang. The problem is when you make that prediction, it is lower than when you make the direct observation. My colleagues and I measured distances and redshifts the same way Hubble did, only with better telescopes. And there's about a 5 sigma discrepancy between these at the moment. So, it seems to indicate that there's something that we are missing. Now, the big question mark in all this is we are using a model called lambda CDM to go from this point in the curve to this point in the curve. The model lambda CDM is what allows us to draw this curve. And lambda CDM is our description of the universe. It's the standard model. Around the time of the Big Bang, the universe would have been mostly dark matter, neutrinos, photons, and atoms. As it slowly evolved and dilutes, it becomes more dark energy and atoms. So if there's something not right about that description, if it's not as simple as that, or there's another feature or wrinkle to this, then it is possible that this trajectory is not right. That's at least what many people are trying to study, while many of us also look very carefully at the measurements. And this isn't just an academic question even about the model. I mean, it really gets back to basic questions like, how old is the universe? Well, I need to know this trajectory to be able to go back in time. And, really this big question of what we're missing. So as I get towards wrapping up, the last several decades have been a phenomenal time in cosmology. We have certainly learned a lot. And, as an optimist, you could say certainly the glass is half full. I mean, we have a standard model of cosmology, lambda CDM, that's very successful, kind of akin to the particle physicist standard model of particle physics. However, we have to acknowledge that about 95% of it is still in unknown forms, dark matter and dark energy, whose nature we don't really understand. This is the stuff that produces the attractive gravity in the universe. This is the stuff that produces the repulsive gravity in the universe. It has a place in our physics, but we don't know it at a deep level. So that's a lot of progress, but then we have these tensions which are emerging in the model. Like, for example, when you look at something going from one direction from the beginning versus to the end, you ought to get the same answer, and we don't seem to. So that might be evidence of a new feature in the universe or some complexity in the model. Whenever we get stuck in my field, the answer always is more data is needed. And so that is certainly the case here. And so there are new missions and new facilities which are on the way, particularly a couple of space telescopes that I'm focused on. One built by the Europeans called Euclid, which launched just a year ago and is on the sky, and one called the Roman Observatory. These are both like the Hubble Space Telescope in scale, but they're largely dedicated to studying this dark energy question. And so in the next decade, I'm expecting or hoping for answers. They have the ability to measure or discriminate between those three hypotheses, that it's a cosmological constant, that it's a field, or that it's a breakdown in gravity on the largest scales. Meanwhile, we also have another fun toy to play with, the James Webb Space Telescope. This is a new powerful telescope. It's bigger than Hubble, but it's not just that it's bigger. Its other superpower is it's much colder than Hubble. It's placed out at Lagrange point 2, which is 4 times the Earth-Moon distance, and it has a giant solar shade which blocks the light of the sun and allows the telescope to get down to a few degrees above absolute zero. Why do we need such a cold telescope? Because we are observing very high redshifted objects. We are observing them in the far infrared as a result. And if you've ever noticed, things like night vision goggles can actually observe the glow from people. Their heat produces infrared radiation as well. So you need a very cold telescope so you're not producing heat from your telescope, which becomes noise or a background that would make it difficult to see the distant objects. So JWST is working very well. Here actually is a deep image taken with Hubble versus JWST. You can see it going a lot deeper. And I am studying nearby stellar fields in galaxies to measure distances. And, I'm trying to measure stars in this image with Hubble, and then I get this image to work with JWST. It's pretty dramatic improvement. So, we are certainly getting better and better measurements, and so that's likely to help in the near future. Okay, so let me just finally wrap up with, why are we so interested in dark energy? It sounds a little esoteric, but first of all, it's 70% of the universe. It's hard to say we understand the universe if we don't understand the biggest part of it. It's also key that it lies right in the critical path to understanding the origin and fate of the universe. In fact, we invoke something like dark energy at other points in the history of the universe, like shortly after the Big Bang. But I think most importantly is we have two great theories of physics. We have quantum theory and we have general relativity. One is sort of physics of the small and one is physics of the big. We know they're not compatible. We know they're not, and people work on trying to figure out how the universe does physics at that interface. So the case of dark energy is actually showing us somehow how the universe is doing physics at that interface. And so it makes dark energy a very important example to study. The fact that it so breaks our understanding, 120 orders of magnitude, means that it must be a very good clue. And so it's likely to lead to something interesting. So I will end there with a few summary points, and thank you for your attention.